Hi everyone, welcome back to my lecture. This video is the part 3 of chapter 3.
In this video, you will be introduced to a group of instructions that are used to control the flow of the program, which is the last part of the instruction set. In computer programming, the program is executed instruction by instruction, line by line, like this. Instruction number 1, followed by instruction number 2, number 3, and so on. But sometimes, especially in the complex programs, we may want to skip certain parts, or certain instructions of the program. For example, in this program, after instruction 4, we will test a specific condition, then if the condition is true, we will skip instruction number 5, and go to execute instruction number 6, and so on. However, if the condition is not true, or false, we need to execute instruction number 5, 6, and so on. Or maybe we want to go back to instruction number 2, or any other instruction in the program, depend on our program specifications. To do this, we need a group of instructions that are called program control instructions. In Microprocessor, the program flow control is realized by the decisions and conditional branches. Most conditional branches in ARM processors use the condition flags to determine whether a branch should be carried out. Recall that, there are 5 condition flags, 4 of them are used for branch decisions, which are the N, Z, V and C flags. There is another flag, called the Q flag. It is for saturation math operations and is not used for conditional branches. With combinations of the 4 flags, the N, Z, C, and V, 15 branch conditions are defined. Using these conditions, branch instructions can be written as below. BEQ, or branch if equal, means if the condition is true, in this case if the result if equal to 0, or Z equals to 1, the program needs to go to the program line marked as label in the program. These are the 15 branches instructions, where 14 of them are the branch with condition, and the last one is the unconditional branch. For all of these instruction, you need to put B in front of this 2 characters. For example, EQ, the instruction is BEQ, branch if equal. NE is BNE, or branch if not equal. Branch with condition, mean the program must branch, if the condition is true. Meanwhile, for the unconditional branch, the program will always branch to the label when it is executing the branch instruction. Here in this column, shows the condition for each branch instruction. For example, the BEQ, the condition is equal, means branch if equal. And it is true when Z flag is set. The BNE, where the condition is branch if not equal. It is true when the Z flag is clear. The BCS, branch if carry set, or we also can use BHS, branch if higher of same for unsigned number, where the condition is true when C flag is set. For all the other branch instructions, you can refer to this table. In the exam, this table will be given. Note that, for branch always, there is no condition to be tested. We have learned some of the most important ARM instruction set. Now, we will learn how to write an assembly program using the instruction set that we have learned. However, before we can write our assembly program, we need to know some of the requirements in writing the assembly program. One of these requirements is the assembly directive. Assembly directives are instructions to the assembler for creating areas of code, aligning data, marking the end of your code, and so forth. These are unlike processor instructions, which tell the processor to add 2 numbers or jump somewhere in your code, since they never turn into actual machine instructions. In other words, they are not part of instruction set. They are command to tell some important configurations for the assembler. This table lists some of the commonly used assembly directives. For example, area, used to define a block of code or data in the program. EQU or equate, used to equate a symbol to a numeric constant. Entry. To declare an entry point to the program. DC are defined contents, where we have DCB, DCW, and DCD. It is used to allocate memory and specifies initial runtime contents. Align. To align data or code to a particular memory boundary. End. To designate the end of the program. An export is used by the linker to combine object file, etc. This is how the assembly program looks like. Here we have the assembler directives. We also have another assembler directive DC here, and the last one is the end directive. We have 4 fields, where the first one is for label. Here we have the main label, stop, and data1 labels. The second field is the mnemonic or the opcode field. The third one is the operand field, and the last one is the comment field. To comment, you need to put semicolon in front of your comment, such that the compiler will not read this section. Note that the comment is very important in programming, as it is used as references by yourself or other programmer. Therefore, please practice to write comments when you writing your computer program. Also, note that the color of your code is different, depend on the type of your code. For example, the operands are blue, registers are green, numbers are red, etc. Now, let's look at how we use the DC to allocate the memory and specifies the initial runtime contents. This is actually the directive to predefine the data in the memory before the program is executed. For example, in the memory starting from address hex 100 to hex 103, we want to have the initial data byte, hex 10, 11, 12, and 13, then we can use DCB hex 10, 11, 12, and 13. We can name that memory location as my data like this. We also can define the memory content with the alphabet. For example, DCB hello. This will be represented in ASCII representation in the memory. Hex 48 represent H, 45 for E, and so forth. For defining half-word size data in the memory, we need to use DCW. For example, DCW hex 1011, hex 1213. The predefined data in the memory will be arranged like this. Address hex 100 will have hex 11. Hex 101 will have 10. Remember? This is due to little endian representation using by ARM architecture. And for the next half-word, address hex 102 and 103 will have hex 13 and 12, respectively. For the word data size, we will use DCD. For example, DCD hex 10111213 will be in the memory starting from hex 13, follows by 12, 11, and 10.
Now, let's look at some of the useful techniques in writing assembly language. For example, how to move an address into a register. Let's for example we want to load the first address of my data into R0. The instruction is LDR, R0, and follow by my data. Assume that the first address of my data is hex 100. Therefore, when we execute the instruction, hex 100 will be in R0. If there is no equal sign before my data, like this instruction, the data in the address hex 100 will be moved to R0 instead. In this case, the data is hex 10, thus, R0 will get hex 10. OK, now let's see how we use the control instruction to write assembly language. For example, to implement the if, then, else statement. If we have C code like this, if A greater than B, C equal to 1, else C equal to -1. This can be represented using this flowchart. If A greater than B, we do this. Else, we do this. In assembly language, first we need to compare the two numbers. Let's assume A is in R0, B is in R1, and R2 is used to store C. The CMP instruction is the compare instruction, where it is equivalent to sub S instruction. However, the compare instruction will not affect the content of register, but will set the condition flags depending on the subtraction result. So, for this example, when we compare R0 to R1, this means R0 minus R1. The next instruction is BGT, means that the program will branch if R0 is greater than R1, or in other words, the result from R0 minus R1 is positive. Therefore, if R0, or A greater than R1, or B, we need to branch to the label next one, where we will move value 1 to R2, or C. But if R0 is less than R1, means, the condition is not true, therefore, no need to branch, hence, we need to move -1 to R2. Now, observe that, we need to skip the next instruction here, because, it will move value 1 to R2 again. So, in this case, we need to use the unconditional branch, B to next 2 and execute the rest. For the for loop statement, for example, if we want to fill in an array of data from A1 to A9, we can write the C code like this. For I equal to 1, and while I less than 10, I plus plus. Then, I equal to the data, in this case, hex F0. This means that, if I equals to 1, then A1 equals to F0, and I is equals to I plus 1, which is 2. Because I equals to 2 is less than 10, then the loop is still continue to A2, A3, until A9 before we can go out of the loop. This process can be illustrated using this flowchart. We can see that I starts from 1, and if I is still less than 10, the process here, assigning F0 to I and I equals to I plus 1 is continue, until we have I is not less than 10 anymore. For the assembly language, let's R0 represents I, and the memory address pointed by R2 represents A. We can have something in the memory like this. Assume that address hex 101 is for A1, hex 102 is for A2, until 109 for A9. Then we have hex 101 in R2 like this. Now, let's the hex F0 is in R1, therefore, we can use store with post-indexed addressing mode like this. This means, we move hex F0 from R1 to the memory address pointed by R2, where the initial value is hex 101. The first F0 will go to address hex 101, or A1 in our case, then update the value in R2 to hex 102, because the index is 1. This is equivalent to I equal to I plus I in C programming. Then we add 1 to R0, or I with 1, and we compare with 10. If less than 10, we need to go back to loop, to do this again, until R0 is not less than 10. Then the process is done. This is a while statement, and this is an example of using the while statement, where in this example, we set a initially equal to 10, then, while a is not equal to 0, therefore, we reduce a by 1. Here is the flowchart. The condition is, whether a is equal to 0 or otherwise. If a equal to 0, then the loop is finished, otherwise, we need to reduce a and go back again. Now, let's look at the equivalent assembly code. R0 is now represent A. We reduce R0 by 1, and we test if the content of R0 is not equal to 0 by using BNE instruction, or branch if not 0 to the label loop. Therefore, if R0 is not equal to 0, then we go back to loop. Now let's look at the practical application. Since any real code will have something more than just arithmetic and control instructions, the whole notion of looping through code needs to be addressed. We need the ability to execute a section of code multiple times, so we're going to start off the discussion of loops by looking at a real problem. Suppose that we want to move a block of data from memory address location hex 20 million to hex 20,001F to a memory address location hex 20,020 to 20,003F. This illustrates what we want to do. So this is the memory spaces that we want to move the data, from memory address hex 20 million, to address hex 20,020. Hex 20,001 to hex 20,021. Hex 20,002 to hex 20,022, and so on, until hex 20,001F to hex 20,003F. Therefore, after we run the whole code, we will have the data from this block of memory to this block of memory. From the memory view, in the Kyle Micro Vision, we can see that the size of the data from address hex 20 million to hex 20,001F is 8 words. From address 20 million to 20,003 is 1 word. Here is another word. 3, 4, 5, 6, 7, and 8 words. Therefore, we can plan our program by using this flowchart. Let's see how it works. We will use the indirect addressing modes with index, where R0 and R1 are used as a based address for address hex 20 million and 20,020, respectively. R3 will be used as a counter, to count whether we have moved up to 8 words or not. Now, here is the moving process, where we move the content of memory address pointed by R0, which is hex 20 million, to R2. Then, we update the content of R0 by adding number 4 to R0, which means, point to the next word. Remember, one word is 4 bytes. That's why we need to add R0 with 4. Now, from R2, we'll move again to the memory address pointed by R1, which is hex 20,020. And again, we update the content of R1 by adding 4 to R1, to point to the next address. Then, we update the counter, by adding 1 to R3. After that, we check whether we already have moved 8 words of data. If not, then we need to go back, to move the next word, until we reach 8 words. When we have reached 8 words, then the process is finished. In this example, I move 1 word at a time. You can move half-word, or byte at a time, but the process will be slower. For example, if you move using half-word size, you need to move 16 times. Meanwhile, if you move using byte size, then you will need 32 times. Here is the assembly program for example 1. The first 4 lines is to set the pointer, where we move hex 20 million and hex 20,020 to R0, and R1, respectively. Then we clear the counter. After that, we move the data from the memory address pointed by R0, into R2 using the LDR instruction because the data is moved from memory to CPU register. We use post-indexed addressing mode here, where the offset is 4, means 1 word. Now, we move the content of R2 to the memory address pointed by R1 by using the same addressing mode, but here we use the STR instruction because the data is moved from register to memory. Then, we update the counter, by adding 1 to R3. Then, we compare R3 with 8, if not equal, means we not reach 8 word yet, therefore, we need to go back, move the data again, until we reach 8 word, then the process is done. Let's look at example number 2. Suppose that we had a register containing a binary value that needed to be normalized. In other words, we need to have the leading one in the most significant bit. Here is how the process. If we have a 32-bit hex number in a register, for example hex 1234, like this. Then we need to do the logical shift left, until the most significant bit gets logic 1, like this. Then, we stop. The programming part is quite easy, where here is the flowchart to implement the process. First, we check whether the MSB is equals to 1 or not. If it is equals 1 already, then no need to do anything. The program will end immediately. However, if the MSB is not equals to 1, then we need to do the shift left, and check again, until we have 1 in the MSB. And here is the assembly program. We use hex 1234 as the data to be checked. We use MOVS here, from R0 to R1, such that the condition flag is updated. In this case, we test n flag by using BMI instruction. If n equals to 1, means the condition is true, then we will jump to done label. If it is not 1, then we need to do the logical shift left here. Observe that we use LSLS, where this logical shift will update the condition flags. Again, we check here, whether n equals to 1, or MSB is 1 or not. If not, we need to go back, and shift again. If yes, the process is done here. Alright, that will be the end for this part 3. In the next lecture, which will be the last part of this chapter, we will learn how the microprocessor executes the subroutine, which is a sub-program in a program. We will learn the function of stack and the link register during the execution of subroutine. Goodbye for now, have a nice day.